Look at the device you are using right now, a glowing rectangle, seamlessly rendering moving shapes, colors, and shadows, instantly transporting your vision to another part of the globe or into an entirely fabricated world. Today, the screen is so ubiquitous that it has become almost invisible to us as a piece of technology. We look through it rather than at it. But the journey to create this glowing rectangle was one of the most agonizing, fiercely contested, and brilliant engineering sagas in human history. The word itself, television, is a hybrid. It combines the Greek word tele, meaning at a distance, and the Latin word visio, meaning to see, distant seeing. For thousands of years, humans could only see as far as the horizon. To understand the sheer impossibility of television in the late 19th century, we must first understand how humanity had conquered other forms of communication. In the 1830s, Samuel Morse and other pioneers proved that we could translate the alphabet into electrical pulses and send them across oceans through copper wires. The telegraph was a miracle, but it was essentially a digital system of dots and dashes, on and off. In 1876, Alexander Graham Bell's telephone proved we could do the same with the human voice. Sound, unlike a letter of the alphabet, is a continuous wave of changing air pressure. Bell figured out how to translate the physical vibration of sound waves into a continuously fluctuating electrical current. But whether it was a telegraphic dot or a telephonic voice, both methods relied on sending a single, continuous stream of information down a single wire. Vision was an entirely different, astronomically more complex problem. You can send a voice down a single wire because sound happens sequentially in time, but an image does not happen sequentially. A single picture is composed of thousands, if not millions, of tiny points of light, shadow, and color, all existing simultaneously across a two-dimensional plane. If you want to send a picture through a single wire, you cannot send the whole thing at once. You have to figure out a way to dismantle the image, chop it up into thousands of microscopic pieces, send those pieces one by one down a copper wire in a perfectly ordered sequence, and then flawlessly reassemble them on the other side. And if you want moving pictures, you have to perform this entire dismantling and reassembling process so incredibly fast that the human eye does not notice the trick. The foundation for this impossible trick was discovered entirely by accident in 1873 by an English electrical engineer named Willoughby Smith. Smith was the chief electrician for the Telegraph Construction and Maintenance Company. He was working on a monumental project, maintaining the transatlantic telegraph cable, a massive copper wire laid across the treacherous floor of the Atlantic Ocean. Smith needed a material with a very high electrical resistance to use as a testing circuit for the underwater cables. One of the materials he experimented with was the element selenium, a nonmetal discovered decades earlier in the residue of sulfuric acid production. Smith had his technicians shape the selenium into small crystalline rods. During his tests, Smith noticed something bizarre, something that defied the known rules of electrical physics at the time. When the selenium rods were kept in a dark box, they acted as a strong insulator, completely blocking the flow of electricity exactly as Smith intended. But when the lid of the box was opened and sunlight hit the selenium, its electrical resistance suddenly plummeted. It allowed electricity to flow freely, and the brighter the light, the more electricity it allowed through. This was a world-changing revelation, the first recorded observation of the photoelectric effect in a solid material. Selenium possessed the magical, natural ability to translate light into electricity. For the first time in human history, engineers had a physical mechanism to convert the brightness of a shadow or the glare of a sunbeam into a fluctuating electrical signal. Almost immediately, inventors across the world realized the implications. If you could turn light into electricity, you could, theoretically, send an image over a telegraph wire. In the late 1870s, inventors like George Carey in the United States and Constantin Senlec in France proposed telectroscopes. Their idea was to build a massive wall of thousands of individual selenium cells. Each cell would act like a modern pixel. When light hit the wall, each cell would generate a current based on how much light it received. But there was a fatal flaw in this early design. To transmit the image from Carey's wall of selenium cells to a receiving wall of light bulbs, every single cell required its own dedicated copper wire. To send an image with the resolution of a modern television, you would need a cable containing over 2 million individual wires. It was an engineering impossibility. The solution to the too many wires problem came in 1884 from the mind of a 23-year-old German university student named Paul Gottlieb Nipkow. Nipkow was sitting alone in his rented room in Berlin on Christmas Eve, staring at the flickering flame of an oil lamp. When he experienced a flash of pure mechanical genius, he realized that to send an image over a single wire, you couldn't look at the whole picture at once. You had to scan it. You had to trick the eye by taking advantage of a biological loophole called the persistence of vision. The human retina is not a perfect biological camera. It holds on to an image for a fraction of a second after the image disappears. If you flash a sequence of images faster than the retina can clear them, usually around 16 to 24 times a second, the brain is fooled. It blends the sequential flashes together into an illusion of seamless motion. Nipkow designed a device to exploit this loophole. He called it the electrical telescope, but history remembers it as the Nipkow disc. It was elegantly, brilliantly simple. Imagine a flat, circular disc made of metal or heavy cardboard, perhaps a foot in diameter. Nipkow punched a series of small square holes into the disc. Crucially, the holes were not arranged in a perfect circle. They were arranged in a spiral, starting near the outer edge and spiraling inward toward the center of the disc. Here is exactly how the machine worked. You place the spinning disc in front of the object you want to televise. Let us say a person's face. You shine an incredibly bright, blinding light onto the face. Behind the spinning disc, you place a single, highly sensitive piece of selenium connected to a wire. As the disc spins, the first hole, located near the outer edge, sweeps across the very top of the person's face. Because the rest of the disc is solid, the selenium only sees the light passing through that one specific hole. The hole allows a single, thin line of light to pass through. As the hole sweeps across the bright, reflective forehead, the selenium sends a strong electrical pulse down the wire. As it sweeps across the dark hair, where less light is reflected, the selenium sends a weak pulse. Once the first hole finishes its horizontal sweep across the top of the face, it rotates out of the frame. In that exact fraction of a second, the second hole in the spiral rotates into place. Because it is slightly closer to the center of the disc, it sweeps a new line just millimeters below the first one. In one complete revolution of the disc, the spiral of holes scans the entire face, line by line, from top to bottom. The image has been rasterized, chopped into horizontal lines, translated into fluctuating electricity by the selenium, and sent down a single wire as a sequential stream of data. At the receiving end of the wire, another Nipkow disc spins at the exact same speed, in perfect, locked synchronization with the first one. But instead of a selenium cell behind the receiving disc, there is a light source. In early designs, a rapidly fluctuating neon lamp. The fluctuating electrical signal coming from the sender causes this receiving lamp to flicker brightly and dimly in exact proportion to the light that hit the selenium. As the receiving disc spins, the viewer looks through the spiral of holes. The flickering lamp paints the lines of the image back into the viewer's eye, one by one. First the forehead, then the eyes, then the nose, then the mouth. If the disc spins fast enough, the persistence of vision takes over. The lines blend together, and the viewer sees a complete, moving, two-dimensional image built from a single wire. Paul Nipkow patented his masterwork disc in 1884. He had laid the absolute mechanical foundation for television. Every screen you look at today, from your smartphone to your cinematic living room display, still uses Nipkow's fundamental concept of rasterization, drawing an image line by line, incredibly fast, from top to bottom. But Nipkow never built a working model of his machine. He couldn't. In 1884, the electrical signals generated by raw selenium were incredibly weak. Without a way to boost or amplify that faint electrical whisper, the signal would die in the wire long before it reached a receiver. Furthermore, the lamps of the 1880s could not flicker fast enough to paint the image back into the eye. Nipkow's patent eventually expired. He became a railway engineer, living a quiet quiet, unassuming life, entirely unaware that his Christmas Eve revelation in a lonely Berlin apartment would eventually change the fundamental fabric of human society. The world would have to wait 40 years for technology to catch up to his spinning disc. The missing link between Paul Nipkow's theoretical spinning disc and a working television was the vacuum tube amplifier, invented in 1906 by Lee DeForest and known as the Audion. This delicate glass bulb could take a microscopic, whispering electrical current and boost it into a roaring signal without losing its shape. By the 1920s, the vacuum tube had matured, allowing radio to blanket the globe. It also meant that the faint electrical signals generated by selenium or newer, more advanced photoelectric cells could finally be amplified enough to travel over long distances or even be broadcast over radio waves. The global race to build the first working television had officially begun. In the United States, well-funded corporate laboratories and brilliant inventors like Charles Francis Jenkins were pouring resources into the problem. But across the Atlantic, the most fiercely determined competitor was a chronically ill, near-destitute Scottish engineer named John Logie Baird. Baird was the quintessential eccentric inventor. Before turning his attention to television, his life had been a string of spectacular, often bizarre commercial failures. He had tried to invent a glass razor blade that wouldn't rust, but it shattered in use. He created pneumatic shoes with inflated soles to soften the impact of walking, but they burst on the pavement. He even moved to the Caribbean nation of Trinidad to start a jam-making factory, an endeavor that ended with his wooden hut being overrun by millions of tropical insects attracted to the boiling sugar. Broke, suffering from chronic ill health, and living in a cheap boarding house in the English seaside town of Hastings in 1923, Baird turned his obsessive focus back to the dream of distant vision. While the corporate labs in America were working with custom-milled steel and precision glass, Baird was working with absolute scrap. His first prototype was a testament to desperate, manic ingenuity. The motor required to spin the heavy Nipkow disc was salvaged from a discarded, broken electric fan. The disc itself was cut out of heavy cardboard scavenged from an old hatbox. The lenses he used to focus the light were bought second-hand from a local bicycle shop, originally intended for bicycle headlamps. The entire rickety contraption was held together with darning needles, scrap wood, sealing wax, and pieces of an old biscuit tin. Baird's early experiments were not just frustrating, they were physically dangerous. To get enough light to bounce off an object, pass through the tiny spinning holes of the disc, and register on his primitive photoelectric cells, he had to use massive, intensely hot arc lamps. The heat generated in his tiny laboratory was suffocating. If he tried to televise a human face, the heat from the arc lamps would literally scorch their skin, burn their hair, and blind their eyes within seconds. Because he couldn't use a live human being for his endless testing, Baird used a ventriloquist's dummy. He named the dummy Stooky Bill. Stooky Bill had brightly painted, exaggerated features with harsh contrasts, heavy black makeup around the eyes, and a bright white painted face. Baird designed the dummy specifically to give his primitive, insensitive photoelectric cells the clearest, highest contrast signal possible. For months on end, Baird sat in his sweltering, jury-rigged lab, spinning his cardboard discs, adjusting his salvaged lenses, and trying to transmit the painted face of Stooky Bill from a transmitter on one side of the room to a receiver just a few feet away. His landlord eventually kicked him out after a high-voltage mishap resulted in a massive explosion that shook the entire building. Baird moved his operation to the Soho district of London, working day and night, and then, on October 2nd, 1925, he finally achieved the breakthrough that had eluded humanity for half a century. Baird tuned his receiver and looked through the spinning disc. Through the flickering, noisy mechanical static, he saw it clearly. The unmistakable, recognizable face of Stooky Bill. It was a crude, 30-line grayscale image, updating at just 5 frames per second, but it was there. It was the first true, recognizable television picture in history. Thrilled and shaking with adrenaline, Baird knew he needed a human subject to prove the machine wasn't just working with high-contrast paint. He immediately ran downstairs to a nearby office and found a 20-year-old office clerk named William Tainton. Baird dragged the bewildered young man upstairs, sat him in front of the blinding, scorching arc lamps, and told him to sit perfectly still. Baird ran to the receiving room. He looked through the disc. Nothing. The screen was a blur of static. Panicked, Baird ran back into the transmitting room, only to find that Tainton, terrified by the blinding light and the searing heat of the lamps, had backed away from the lens to save his face. Baird pulled out a half-crown coin, paid the young man on the spot, and begged him to endure the heat for just a few seconds longer. Tainton leaned back into the blistering light. Baird sprinted back to the receiver, and there, emerging from the mechanical flicker, was the faint, ghostly, moving image of William Tainton's face. He was blinking, he was moving his mouth. Tainton had just become the first human being in history to be televised. Baird's mechanical system was a marvel of perseverance, but its limitations were staggering. The 30-line resolution produced an image roughly the size of a postage stamp. It was blurry, distorted, and required intense concentration just to figure out what you were looking at. Yet, when Baird gave the first public demonstration to members of the Royal Institution and a reporter from the Times newspaper in January 1926, the public was mesmerized. The sheer magic of seeing a moving human face transmitted through the ether superseded the terrible quality of the image. Baird capitalized on the momentum. He was a relentless self-promoter. By 1928, utilizing immense shortwave radio transmitters, Baird managed to send a television signal across the entire Atlantic Ocean, broadcasting a recognizable human face from London to a receiving station in Hartsdale, New York. It was a stunt, heavily distorted by atmospheric interference, but it proved the global potential of the medium. He even developed early, incredibly crude versions of color television by stacking 3 spinning discs together, each fitted with red, green, and blue gelatin filters. He demonstrated stereoscopic 3D television and even developed a system called phonovision. Because his early 30-line television signal operated at a very low frequency, Baird realized the signal could actually be recorded as audio. He pressed the television signals into regular wax vinyl records. If you played the record on a normal phonograph, it sounded like a chaotic, high-pitched screech, but if you routed the audio output of the record player into a Nipkow disc receiver, the screeching noise decoded back into a flickering video image. He had inadvertently invented the first video recording format, decades before magnetic VHS tapes. But as the 1920s bled into the 1930s, the fundamental, fatal flaw of mechanical television became impossible to ignore. It was hitting a hard, unbreakable wall of physical physics. The problem was resolution. A 30-line image was a novelty, but you couldn't broadcast a play, a newsreel, or a sporting event with 30 lines. It was a blurry mess. To get a sharper, cinematic picture, you needed to chop the image into more lines. More lines meant you needed more holes in the Nipkow disc, but you couldn't just punch more holes in the same small disc because the holes would begin to overlap, destroying the scanning sequence. To add more holes, the disc itself had to be physically larger. Furthermore, to create smooth motion, the disc had to spin incredibly fast. To avoid a flickering, headache-inducing strobe effect, the image needed to update at least 25 to 30 times a second. Baird's 30-line image, spinning at a low frame rate, required a reasonably sized disc that a small electric motor could easily turn. But if you wanted an image with the clarity of a modern television, say 500 or 1000 lines of resolution, updating at 30 frames per second, the mechanical math became utterly terrifying. To achieve high-definition television mechanically, you would need a Nipkow disc the size of a 2-story building, and to achieve 30 frames per second, the outer edge of that massive, building-sized metal disc would have to spin at supersonic speeds. At those velocities, the sheer centrifugal force would cause the metal to warp, buckle, and eventually shatter like glass, sending lethal shrapnel tearing through the studio and destroying the equipment. Mechanical television was a dead end. Heavy spinning discs and whining electric motors were simply too slow, too fragile, and too bound by the laws of friction and momentum to handle the sheer, immense volume of data required for high-definition moving pictures. If television was going to enter the home not as a flickering, postage stamp novelty, but as a clear, reliable, high-resolution window to the world. Engineers had to throw away the spinning discs entirely. They had to abandon heavy, moving physical parts. They needed something that could scan an image at the speed of light, with zero friction and zero mass. They needed to harness the fundamental building blocks of the universe. They needed the electron, and the man who would figure out how to tame it was not a well-funded corporate scientist in New York, nor a manic inventor in a London boarding house, but a 14-year-old farm boy driving a horse-drawn plow through the dirt of Idaho. In the summer of 1921, a 14-year-old boy named Philo Taylor Farnsworth was driving a horse-drawn cultivator through his family's potato farm in Rigby, Idaho. Farnsworth was not a typical farm boy. He was a mechanical prodigy, a self-taught science enthusiast who spent his evenings reading advanced physics journals by the dim light of a kerosene lamp. He had read all about the mechanical television experiments happening in Europe and on the east coast of America. He understood the fundamental problem with Paul Nipkow's spinning disk. Physical objects have mass, and mass creates momentum and friction. A spinning disk was simply too slow and too heavy to ever scan an image fast enough to produce a clear, high-definition picture. As Farnsworth reached the end of a row and turned his horses around, he looked back over his shoulder at the potato field. He saw the pattern he had just cut into the dark earth. The field was perfectly, geometrically divided into parallel, horizontal rows. In that moment, staring at the dirt, Farnsworth had a vision of pure, unadulterated genius that would alter the course of modern history. He realized that you didn't need a spinning physical disk to scan an image line by line. You could use something that weighed virtually nothing, something that was not bound by the friction of bearings or the shattering force of centrifugal motion. You could use the electron. Electrons are subatomic particles carrying a negative electrical charge. Because they have virtually zero mass, they can be accelerated to a massive fraction of the speed of light. And because they carry an electrical charge, their path can be instantly bent, pushed, and pulled by magnetic fields. Farnsworth envisioned a completely sealed glass tube with all the air sucked out of it, a vacuum tube. At the narrow back end of the tube, an electron gun would fire a continuous, concentrated beam of electrons toward the wide, flat glass front of the tube. The inside of this front glass would be coated with phosphor, a chemical compound that glows brightly for a split second when struck by an electron. Here was the breakthrough. Instead of moving the glass screen, you move the beam. By placing electromagnetic coils on the outside of the glass tube, you could magnetically steer the electron beam. You could use the magnetic fields to make the beam sweep across the phosphor screen from left to right, line by line, exactly like a plow cutting rows into a potato field. Once it reached the bottom, the magnets would instantly snap the beam back to the top left corner to start again. Because electrons are practically weightless, the magnetic fields could sweep the beam across the screen hundreds of thousands of times a second. No friction, no shattering metal discs, absolute high-definition electronic scanning. This device is known as the cathode ray tube, or CRT. Every thick, heavy, box-like television and computer monitor of the 20th century was essentially a CRT. When you sat in your living room watching a CRT television in the 1990s, you were literally staring down the barrel of a localized domestic particle accelerator, watching a magnetically steered beam of subatomic particles paint an image in glowing phosphor onto a lead-lined glass shield. The very next day, Farnsworth ran to his high school chemistry teacher, a man named Justin Tolman, and sketched his entire complex electronic television system on the classroom chalkboard. Tolman was astounded by the teenager's grasp of quantum physics and electronics. He carefully copied the chalkboard sketch onto a piece of paper and tucked it away. That faded piece of paper would eventually become one of the most important documents in the history of global patent law. By 1927, operating out of a heavily shaded makeshift laboratory in San Francisco, funded by a few brave local investors, a now 21-year-old Philo Farnsworth successfully transmitted the first all-electronic television image. It was not a face, but a simple, single, horizontal black line painted on a piece of glass. When his brother-in-law turned the glass 90 degrees, Farnsworth, watching the receiver in the next room, saw the line on his screen turn 90 degrees. It was a flawless, entirely electronic transmission. His camera tube, which he called the image dissector, worked, but Farnsworth was about to learn a brutal, heartbreaking lesson about the intersection of pure science and corporate warfare. On the East Coast, David Sarnoff, the ruthless visionary executive who ran the Radio Corporation of America, or RCA, understood that television was the inevitable successor to radio. Sarnoff had practically limitless funding, and he had hired a brilliant Russian immigrant scientist named Vladimir Zworykin. Zworykin was working on a very similar electronic camera tube called the iconoscope when Sarnoff learned that a farm boy in a California garage had beaten RCA's multi-million-dollar laboratory to the foundational patent for electronic television. He deployed an army of corporate lawyers. Sarnoff's business philosophy was famously simple. RCA does not pay royalties. RCA collects them. For an entire decade, RCA dragged Farnsworth through agonizing, expensive patent litigation, attempting to bleed his small company dry. They claimed that Zworykin had invented the electronic system first, pointing to a vague patent application Zworykin had filed years earlier, even though Zworykin had never actually built a working prototype at that time. The corporate war culminated in a dramatic patent hearing. The determining factor came down to a single historical question. Who could definitively prove they had the concept for electronic scanning first? RCA's lawyers were confident, but Farnsworth's lawyer called a surprise witness to the stand. It was Justin Tolman, Farnsworth's old high school chemistry teacher. Tolman pulled a faded, crumpled piece of paper out of his pocket. It was the exact sketch Farnsworth had drawn on the chalkboard years earlier in Idaho. He explained to the patent examiners exactly what the 14-year-old boy had described to him. It unequivocally proved Farnsworth had conceptualized the electronic system years before RCA or Zworykin. Farnsworth won. He had slain the corporate giant. RCA was forced to do something it had never done in its history: sign a licensing agreement and pay running royalties to an independent inventor. It should have been a moment of ultimate triumph and unimaginable wealth for Philo Farnsworth, but tragedy intervened. Just as electronic television was finalized and ready for massive commercial rollout, in 1939, World War II broke out. The United States government immediately suspended all commercial television production and broadcasting. The glass factories and electronics plants were desperately needed for military radar and communication arrays. By the time the war ended and television exploded into millions of American homes in the 1950s, the brutal reality of patent law struck. Patents only last for a limited time. Farnsworth's foundational patents expired just as the boom began. RCA dominated the post-war market, manufacturing millions of sets and reaping the financial rewards without having to pay Farnsworth another dime. Farnsworth, heartbroken, exhausted by litigation, and largely forgotten by the public, fell into deep depression and obscurity. Yet his potato field revelation remained the beating heart of every television on Earth for the next 60 years. By the early 1950s, black and white CRT televisions were the undisputed kings of the living room. Families gathered around the glowing box to watch news, variety shows, and dramas. But the world outside the living room is not in grayscale. The next great frontier was color, and this inevitable leap forward led to a massive, bitter technological war between two broadcasting giants, CBS and RCA. CBS struck first. They developed a color television system that was, surprisingly, a technological throwback to the mechanical days of John Logie Baird. It was a mechanical-electronic hybrid. They used a standard CRT to display the picture, but inside the television, placed directly in front of the screen, they mounted a physical spinning wheel divided into red, blue, and green transparent filters. The television camera in the broadcasting studio had a synchronized spinning wheel of its own. The camera would capture a red frame, then a blue frame, then a green frame. The television in your living room would receive the signal, and as the wheel spun, it would flash the red, blue, and green images sequentially. Because it happened incredibly fast, the human eye blended them together into a full-color picture. The CBS system produced beautiful, vibrant, saturated colors. In 1950, the Federal Communications Commission, the FCC, actually approved the CBS mechanical wheel as the national standard for color television, but there was a catastrophic, fatal flaw. The CBS mechanical color system was completely incompatible with the millions of black and white televisions already sitting in American homes. If CBS broadcast a program using their color wheel system, a standard black and white television couldn't understand the signal. The screen would just show distorted, unwatchable static. To watch television, Americans would have to throw away their expensive sets and buy entirely new CBS machines. David Sarnoff at RCA saw this vulnerability and launched a massive counterattack. He ordered his engineers at RCA to achieve the impossible, create an all-electronic color television system that was completely backward compatible. He demanded a system where a new color television would display the program in brilliant color, but a regular black and white television would just ignore the color data and display a perfect black and white image from the exact same broadcast signal. RCA's engineers achieved this through a miracle of sub-millimeter precision engineering called the shadow mask. Instead of having one electron gun in the back of the vacuum tube, an RCA color television had three, one for red, one for green, and one for blue. The screen itself was no longer coated in a uniform, solid layer of white phosphor. Instead, the inside of the glass was covered in millions of microscopic phosphor dots, perfectly arranged in triangular clusters of three, one red glowing dot, one green glowing dot, and one blue glowing dot. Just a fraction of an inch behind this glass screen was a thin metal sheet, the shadow mask. This metal sheet was punched with millions of microscopic holes, perfectly aligned with the clusters of phosphor dots on the glass. The three electron guns fired simultaneously. The magnetic coils steered all three beams so they converged and passed through a single microscopic hole in the shadow mask at the exact same time. But because the three guns were positioned at slightly different angles in the back of the tube, once their beams passed through the tiny hole, they spread apart just enough so that the beam from the red gun only struck the red phosphor dot, the blue beam only struck the blue dot, and the green beam. By varying the intensity of each beam, the television could mix red, green, and blue light to create any color in the visible spectrum. It was an engineering nightmare to mass produce. If the metal shadow mask warped even a fraction of a millimeter from the heat of the electrons, the colors would bleed and blur. But RCA perfected the manufacturing process. It worked flawlessly. It was entirely electronic, with no loud, spinning wheels, and crucially, the signal could be read by older black and white sets. In 1953, the FCC reversed its previous decision. They threw out the CBS mechanical wheel and crowned RCA's system as the national standard, known as NTSC. This incredible standard remained the backbone of television broadcasting until the digital transition in the 21st century. For decades, the CRT reigned supreme, but it had undeniable physical limitations because the electron gun had to be a certain distance from the screen to properly sweep the magnetic beam across the wide glass without distorting the corners. A CRT television was fundamentally deep. It was a massive, heavy glass funnel. Furthermore, firing electron beams required massive amounts of high-voltage electricity. If humanity wanted screens on their laps, in their pockets, or hung completely flat on a wall, the domestic particle accelerator had to go. The solution came from an entirely different branch of physics, utilizing a bizarre state of matter discovered in the late 19th century, liquid crystals. In 1888, an Austrian botanist named Friedrich Reinitzer was studying cholesterol extracted from carrots. He noticed that this strange substance had two distinct melting points. At one temperature, it melted into a cloudy, milky liquid, but if he heated it further to a higher temperature, it suddenly turned into a perfectly clear liquid. He had accidentally discovered liquid crystals, molecules that flow and pour like a liquid, but maintain a structured, orderly alignment like a solid crystal. For nearly a century, liquid crystals were just a useless scientific curiosity, but physicists eventually realized these molecules had a magical property. They could manipulate light at the molecular level. Light, as a wave, naturally vibrates in all directions. If you pass light through a polarizing filter, the filter acts like a microscopic picket fence. It only lets light waves vibrating in one specific direction pass through. If you place a second polarizing polarizing filter directly behind the first one, but you turn that second filter exactly 90 degrees. No light can pass through at all. The microscopic picket fences are crossed. The screen goes completely black. The absolute genius of the liquid crystal display, or LCD, relies on sandwiching a microscopic layer of liquid crystals between two of these polarizing filters. When an LCD television is turned on, a bright white backlight shines from the very back of the TV. The light passes through the first polarizing filter and becomes polarized. It then hits the liquid crystals. In their natural, resting state, these specific crystal molecules form a twisted shape, like a microscopic spiral staircase. As the polarized light travels through the twisted molecules, the light wave itself is physically twisted by exactly 90 degrees. Because the light has been twisted 90 degrees by the crystals, it can now perfectly slip through the second polarizing filter, which is set at a 90-degree angle. The light escapes the screen, and the pixel appears bright. But here is the magic. If you apply a tiny electrical voltage to the liquid crystals, they instantly untwist and stand up straight. Now, the light passing through them is no longer twisted. When it hits the second polarizing filter, the cross-hatched picket fence blocks it. The pixel goes completely dark. An LCD television is essentially a grid of millions of microscopic, electrically controlled light shutters. By rapidly applying and removing voltage to individual pixels, the liquid crystals untwist and twist, blocking or allowing light to pass through microscopic red, green, and blue color filters placed over the pixels. There are no massive vacuum tubes, no electron guns, no lethal voltages or heavy lead-lined glass shields. Just a thin sheet of backlight, two polarizing films, and a microscopic layer of cholesterol-like molecules performing a perfectly synchronized, silent electrical dance. From Willoughby Smith's accidental discovery of selenium on the ocean floor, to Paul Nipkow's spinning cardboard disc on Christmas Eve, to Philo Farnsworth's magnetically steered electrons born in a potato field, and finally, to the twisting molecules of the liquid crystal display, the history of television is a testament to our relentless obsession with seeing beyond the horizon. We captured light, turned it into lightning, sent it across the sky, and trapped it behind glass, forever changing how humanity experiences reality. And now, if you are utilizing this video for the dopamine detox challenge, it is time to check your focus. You have just absorbed over a century of incredible engineering and the fierce corporate battles that brought the screen to your living room. Let us see how much your brain retained. Question 1. What was the fundamental mechanical flaw with Paul Nipkow's spinning disc concept when it came to high-definition television? A. It required a disc too massive and spinning too fast to be physically safe. B. It could only transmit in black and white. C. It required lasers that had not yet been invented. D. The cardboard would constantly catch fire. The correct answer is A. It required a disc too massive and spinning too fast to be physically safe. Question 2. Philo Farnsworth realized he could replace the spinning disc with a beam of what subatomic particle? A. Photons. B. Neutrons. C. Electrons. D. Protons. The correct answer is C. Electrons. Question 3. Where was Philo Farnsworth when he had the epiphany to scan an image using parallel lines? A. Working in a watch factory. B. Plowing a potato field on his family's farm. C. Staring at a brick wall in London. D. Riding a train across the country. The correct answer is B. Plowing a potato field on his family's farm. Question 4. What is the primary characteristic of an electron that allowed Farnsworth to sweep it across a screen hundreds of thousands of times a second? A. It emits its own light. B. It is highly radioactive. C. It has virtually zero mass and can be steered by magnets. D. It naturally travels in a perfect spiral. The correct answer is C. It has virtually zero mass and can be steered by magnets. Question 5. What chemical compound is coated on the inside of a cathode ray tube (CRT) glass screen to make it glow when struck by an electron? A. Phosphorus. B. Phosphor. C. Selenium. D. Liquid crystal. The correct answer is B, phosphor. Question 6. Who was the ruthless executive of RCA who waged a decade-long patent war against Farnsworth? A. Alexander Graham Bell. B. Thomas Edison. C. David Sarnoff. D. Vladimir Zworykin. The correct answer is C, David Sarnoff. Question 7. What crucial piece of evidence won the patent war for Philo Farnsworth? A. A photograph of his first working prototype. B. A chalkboard sketch saved by his high school chemistry teacher. C. A signed confession from a corporate spy. D. A telegraph sent to the patent office. The correct answer is B, a chalkboard sketch saved by his high school chemistry teacher. Question 8. What global event halted the commercial rollout of electronic television in 1939? A. The Great Depression. B. World War I. C. World War II. D. The Cold War. The correct answer is C, World War II. Question 9. In the 1950s, CBS developed a color television system that used what mechanism? A. A spinning wheel with red, blue, and green filters. B. 3 separate electron guns. C. A prism that split light into a rainbow. D. Colored liquid crystals. The correct answer is A, a spinning wheel with red, blue, and green filters. Question 10. What was the fatal flaw of the CBS color television system that ultimately led to its downfall? A. The colors were too dim to see in a bright room. B. It was completely incompatible with existing black and white televisions. C. It caused the television sets to overheat and explode. D. It required 3 separate antennas. The correct answer is B. It was completely incompatible with existing black and white televisions. Question 11. To solve the compatibility problem, RCA invented a metal sheet with millions of microscopic holes to precisely guide 3 electron beams. What is this sheet called? A. The color grid. B. The Nipkow filter. C. The shadow mask. D. The pixel gate. The correct answer is C, the shadow mask. Question 12. In 1888, Austrian botanist Friedrich Reinitzer accidentally discovered liquid crystals while studying what substance? A. Tree sap. B. Cholesterol extracted from carrots. C. Bee venom. D. Potato starch. The correct answer is B, cholesterol extracted from carrots. Question 13. Liquid crystals have a unique property that allows them to do what to a light wave? A. Freeze it in place. B. Multiply its intensity by 10. C. Physically twist its orientation. D. Change its speed. The correct answer is C, physically twist its orientation. Question 14. What acts like a microscopic picket fence in an LCD television, only allowing light vibrating in one specific direction to pass through? A. A polarizing filter. B. A shadow mask. C. A phosphor dot. D. A cathode ray. The correct answer is A, a polarizing filter. Question 15. What happens to the liquid crystals in an LCD screen when a tiny electrical voltage is applied to them? A. They evaporate and create a glowing gas. B. They turn solid black. C. They untwist and stand straight up, causing the light to be blocked by the second filter. D. They spin rapidly to create color. The correct answer is C, they untwist and stand straight up, causing the light to be blocked by the second filter. How did you do? If you remembered the correct options for the majority of these details, your focus is sharp and your attention span is recovering. If you struggled, do not be discouraged. Rewiring an overstimulated brain takes time. The most important step is simply putting the phone down and choosing to engage deeply with one subject. Thank you for taking the time to challenge yourself today. Subscribe to the channel, return in 3 days for your next deep dive, and continue taking your brain back.